All right, we're live, people. I'm going to record this just as we go through these notes here, because if you ever want to go back to them, and also some kids were not here today, so then they can get on here and see what we did today in class. Okay? All right. So, I know, right? But just to run through this real quick, I think everybody's probably pretty good with this. You're definitely going to get that 3x squared is 9, right? Okay. And you can do a log there if you want, but 3 to what power is 9? 2. So x squared is better equal 2. And everyone, if you knows, the answer has to be both positive and negative root 2, right? Yeah, there you go. To find the vertex of a parabola, you can do several different things, one of which is, you know that formula to find the vertex? X is equal to negative b over 2a. Okay, you ready? If you didn't know that, or you do know it, you don't know why, all that is the first part of the quadratic formula, right? And the reason why it works, the reason the quadratic formula works, watch this craziness, is if you go to where the let's say we had this, you go to where the vertex is, which is this first part, and then go up and down the second part, that's where the zeros are. Does that make sense? That's why it's a plus and minus. I know, right? You got the vertex, left and right. I know. Okay? So, that's that. I'm going to blow your mind a little more in a second here. Watch this. It's a little deeper here, okay, with quadratics. You can also do it by completing the square, if you remember completing of the square at all. Like if you had x squared plus 8x, the number, remember how to make something a perfect square? It's divided by 2, like the b term, it's half of it squared, okay? The reason that works is because, I'll make up another one. If you take anything and square it like that, you always get double it here and squared it right there. Does that make sense? That's how squaring works. So this being an 8x here, which is what it was right there, means that I need this number here to be a 16. But it's not a 16, it's a stupid minus 3. Okay? Keep in mind that this is, let's see if we can get through this, x plus 4 squared, right? Stick with me here. What's adding 4 to x in the x squared function do? To any function, what's adding 4 to x do? It moves it. Remember, you did all this in algebra 1 and 2. They harp on this a lot. Where's the plus 4 move it? Left 4. So x plus 4 squared, 1, 2, 3, 4. It's just that right there, right? Okay, ready? But we don't have, that's if there's a 16 there. We don't have a 16, we have a minus 3. Which means how much do we take away from that 16 to get to a minus 3? 19. All that did was move, remember, taking 19 away from a function moves it down 19. So this parabola is just all the way down here at negative 4, 19. That's where it has to be. That's all the transformations going on. Negative 19, thank you. You also get that, so if you just do the negative b over 2a situation here, you will get, what, negative 4. If you plug negative 4 into that parabola, you will get negative 19. Is that okay? And then the last little piece about parabolas, wrap this all up, is this. Okay, I did not ask this, but if you can do the work I just did, you can solve any quadratic equation relatively simply. If you move the vertex down 19, what that does, and this is not going to look right because I'm not in the right spot, it moves the 0. Remember, the 0 wasn't negative 4, right? It's moved to a 4. If you move the vertex down 19, it moves the zeros over root 19. So if I ask you what are the zeros to that parabola, without doing any work, you could just tell me it's negative 4 where the vertex is, plus or minus the square root of 19, if that works. Does that make sense? So completing the square is like a really powerful kind of thing, but you guys don't do a lot of that, I don't think, in like algebra 2, right? But you can solve a lot of quadratics pretty simply just by completing the square and knowing where the vertex is. It just does it automatically. I think it's way simpler to doing the whole b squared minus 4ac, all that junk. Anyway, that happens. The capital of Florida is Tallahassee. How to spell Tallahassee? T-A-L-L. Tallahassee. 2 S's? I don't know. Close enough. All right, good. All right, so we are going to take a bullet quiz. I'm going to save it for the end of the class, though, so that we can continue this little video. Okay? All right, we'll just be on straight trigonometry. We're going to talk today our very first really calculus topic. Everything we've done so far is just kind of reviewing algebra stuff, okay? Because that's what students always forget. That's really the hardest part of the class, honestly. The calculus stuff's not too bad. Today we're going to start talking about calculus a little bit. I hope you've seen the concept of limits before. Okay, I'm going to go through kind of slow what it means. All right, so because evaluating them is how we're going to start off our year. But as we get through the year, we're going to stop evaluating them because we don't need to anymore, because there's a rule we can use to kind of bypass it. You just can't learn it yet because you don't know calculus yet. Okay? But what's really important you take with you is the concept of what a limit is actually doing. Okay? So I'll start it off with a pretty easy concept, talking about the function 1/2 to the x power. Okay? That's an exponential function. And as x gets bigger, we just keep multiplying by 1/2. That's what that's supposed to do. Okay, so if I ask you what's f of 1, everybody knows that's just 1/2 to the first power, which is 1/2. Okay, if we did f of 5, that would be 1/2 times itself 5 times. That would give us 1/32. Okay, if I ask you what's f of 10, I have no idea what 2 to the 10th power is. What is it? 32, 64, 128, 256, 512, 1024. 1/1024. There you go. Okay, and what happens is, you can see this happen really quickly. If we do 1/2, you can see on my calculator right, it's there, to the 20th power, you start getting scientific notation. See the e -7 there? That means 0.000000009. Okay, super tiny number. So you can see the pattern here. What's happening to our outputs? They're getting very small, which means they are approaching 0. Okay. So much so that if I put an f of 10,000, you all know that's not 0, right? I cannot multiply by 1/2 and get 0. That's not how math works. Okay, but it's such a small number that the calculator is like, screw it, it's 0. Like it can't handle how tiny it is. Okay, so this is, if you put this in, it just says, yo, it's basically 0. It's so small, it doesn't matter. Okay, but mathematically, that's not true. That's like a shortcoming of a man-made like computer concept, right? The calculator only has so much memory; it can't handle a number that small because it needs all those numbers to get down to it. Just can't do it. Okay, and that's true of like a lot of man-made things, right? Like if you think about like any tablet these days, you can zoom in pretty far, right? Think about that. But eventually, there's a limit to how far you can zoom in. The math number line's not like that. You can zoom in forever and ever, and there'll always be numbers there, no matter how far you zoom in. They'll be there. Okay. And that's what we have this idea of this limit. So we can say that, this makes sense, the limit as we approach infinity, right, is 0. Here's what that means. If I plug in, approaching infinity is not really a thing. X can't get close to infinity. That means X is getting bigger and bigger and bigger and bigger without bound. That's what that means. Infinity is not a number. It just means it's growing forever without bound. Okay? If I plug in bigger and bigger and bigger and bigger numbers, the outputs will get closer and closer and closer to 0. Make sense? It's a basic idea of a limit attached with one other fact. And it's this: how close to 0 can I get? Who can get the closest to 0? Like, you know what I'm saying to you? Like, there is no closest. It can get as close as you want. If I said make this thing 0.00001, you can make it happen. Make sense? So it gets closer and closer to it. And no matter how close you get, you can always get closer. That's the idea of this limit. It's called infinitely close. Okay? So, again, makes sense, never ever 0. And we're just going to, a loose idea of limit for us too, typed it up here. It's what a function's headed towards as x gets really close to some number. Okay? Last example is not great because we're not really getting close to infinity. We're just getting bigger. Make sense? So that leads us to like this discrepancy here a little bit. It's very subtle, and in terms of doing well like this unit and just evaluating things, this is not crazy important, but understanding what's going on, there's like this subtle difference, okay, between this question here. If you look at this little example here, what's the limit as we approach 3 of x plus 4? Think about that versus if f of x is x plus 4, what's f of 3? Okay, so if f of x is x plus 4, and you're asked what's f of 3, you plug 3 and you get 7, okay? The answer to my limit is also 7, but it's not the same question, okay? It seems like the same question, but it's not. The limit question is saying, if you plug in values really, really, really close to 3, how close to 3? Infinitely close, closer and closer and closer. What will the outputs get infinitely close to? And the answer is 7, and that's easy to see because x plus 4 is just a basic function, right? It's a line, okay? It's continuous, which is a key thing for us. But we have this notion that if a function goes to 7, then it must approach 7. Does that make sense? Like if I walked over to the door and I got to the door, I must have approached the door. I can't just be at the door. But functions can. Functions cannot exist. Like, you can't disappear, right? A function can. A function can head towards one number and get to another number. So we need this idea to talk about not just where a function is, but where is it going, okay? That's the idea of a limit. And you see that in my next example down here, as x approaches 2 of this thing, okay, of x squared minus 4 over x minus 2. So the very first thing you should do with any kind of limit you're asked to evaluate is plug in. Because if you get an answer, like in the first example, that's basically your answer. If it goes to 7, then that's what it's approaching. Okay? But what happens most of the time in a calculus class, and I'll show you why later on, why this happens, okay? Or why I have to make it happen, right? You're going to get 0 divided by 0, okay? If you put 2 into this function, you get 0 over 0. And here's what that means. At 2, this function does not exist, okay? But that's not what you're being asked to find. You're being asked to find what's it headed towards, which is different, okay? And if you remember back to your pre-calc days, right? And algebra 2, they do this in rational functions. Remember they used to do rational functions, they give you equations and you graph the top, graph the bottom. Anything that canceled out was a whole, right? So that's what usually happens in the 0 to 0 situation. And also, let me come over here for a second too. We talked about this rule for math too. If we have any, I'm just making up a function right now, okay, to show you a point here. If I plug in, let me see here. What's that? 8 minus 16 plus 8. Okay? If I put 2 into that function, I get back 0. Everybody okay with that? Right? Did I mess up? That's true? No, this has to be a 4. There we go. Now if I put 2 into that function, I get 0. Okay? That automatically means, without me even thinking about it, as I wasn't planning to do it, I just wanted to make sure it was 0. When you factor it, x minus 2 will factor out of there. It has to. It's a mathematical fact, okay? As long as it's all algebra x to powers. If you plug in a value and get 0, x minus that must factor out, okay? So over here, this is a little bit easier example, but the fact that I plugged in 2 and got 0 divided by 0 means x minus 2 has to factor out of the top and the bottom, which means it's going to cancel out, okay? So that's really what your job becomes. When you get 0 over 0, you start thinking, okay, I need to cancel out. And not only do you know you have to cancel out, you know exactly what you have to cancel out, x minus that number, okay? And this example is not hard. Pretty much everybody sitting here, I imagine, knows that this is just going to factor like this. It's okay. You can see it's canceling out. Doesn't matter how complicated it gets. It could be a 10th degree equation. If you plug in 6 and get 0, x minus 6 is going to factor out. So just do synthetic division with a 6 in there. It's going to factor. That's how it's going to go. Okay. You're not going to see any 10th degree equations, but does it make sense that the x minus 2s are going to cancel here? Because x minus 2 over x minus 2 will always cancel unless it's what number? What's the only number that doesn't cancel like that? 0 over 0 doesn't cancel out, right? It's just not a number. But our limit is saying we care about what's happening as we go to 2, not what's happening at 2. So since we care about what's happening at 2, we cross them out, and the limits are still the same. Okay? So this is just 4. You can evaluate like that. So what we just did was we took a function that was semi-complicated, which I'll explain to you why I chose that function later, all right? And we reduced it down by taking the whole away from it, okay? So you all know what x plus 2 looks like? It has a y-intercept of 2, has a slope of 1, right? So if you graphed x plus 2, it would look like that. The only difference between x plus 2 and my original thing is that there's a hole at 2, 4. Graphically, it's really easy to see that if you're riding on this line towards 2, you're headed towards the y value of 4. Am I okay with that? Okay? That's what every time we do a limit, most of the time it's going to be 0 over 0. Okay? Not every time, most of the time 0 over 0. If you plug in and get a number, that's your answer. And our other possibility that we'll see a lot is if you get some other number divided by 0, like 6 over 0 or something. Okay? And then we'll talk about that later on. All right. So one more example before I get into why we're doing what we're doing. If you plug 4 into that, so you get 0 divided by 0, right? Which automatically means x minus 4 has to cancel. Has to. The x minus 4 is already on the bottom. You can see it sitting there. We got to get it out of the top. Okay? So the main kinds of limits you're going to have to handle algebraically are factoring, which is what we just did, right? Y'all can factor things and cancel. The second one is complex fractions. Cool. There's a couple more we'll look at later on in a couple days. Okay, but complex fractions will always be handled like this. A complex fraction is a fraction with fractions inside of it. That's what this is, okay? We don't want those little fractions there. We want to get rid of them. And anytime you want to get rid of a fraction, because a fraction is just division, you get rid of it with multiplication, all right? So I'm going to get rid of this fraction by multiplying by x. I'm going to get rid of this fraction by multiplying by 4, okay? The trick is you got to do it so that you're not changing the value of the whole system we have here. If there's an equal sign, right, if we have an equation, I can multiply both sides by x and 4. Okay, but I don't have an equation here, I just have one expression. So I need to multiply the numerator and the denominator by 4 and x and 4. Okay, so all I'm going to do is attach right here a 4x and a 4x. And when I do that, I'm going to put parentheses around these numerator and denominator, because you're multiplying the whole thing by 4x. Everybody okay with that? So all that does is distribute the 4x to the 1 over x. And you can do that. 4x times 1 over x. Because I'm hoping we don't have to do this. That's 4x over x. It's just 4, right? When you multiply 4x times 1 over x, the x's just cancel. And style-wise, we are still writing limit, okay? Because we haven't done the limit yet. We haven't evaluated it. So we're going to get 4 here. Over here, the 4's are going to cancel, so we get a minus x. Everybody with me? Okay? Okay? In the denominator, I know you guys are programmed to multiply things out and to distribute, but keep in mind what our end goal here is, to cancel out an x minus 4. If I multiply the 4x into that, I'm going to have to factor it back out again. Doesn't make any sense. So don't do it. Make it easy on yourself. Okay? And I'm hoping, again, eventually we can skip this next step. It turns out that if you have 4 minus x over x minus 4, they'll cancel out and they'll leave a negative 1. Okay? It's the same thing as, if you can imagine, I'm factoring a negative out of that, which really just makes it negative x minus 4 is what's going on there, okay? So if you're doing your homework and you see that, like a minus b over b minus a, just cross them out and there's a negative there now. All right? So these cross out, leaving a negative 1, bless you. And we're really left with limit as x goes to 4, negative 1 over 4x. Okay? I try to speak in, like, facts that are always true here. The fact that I just canceled that out means there's a hole at 4. Okay? I just removed the hole. Just bless you. If you plug in 4, you get negative 1 over 16. All that means is the graph of my original thing, let's erase all this junk we put on it, the graph of this thing has a hole at 4, and its y value is negative 1/16, which is super duper tiny. Okay? And actually, so this graph, if you were to graph it, there's something like that. Okay? But it's approaching that hole, so negative 1/16 is the answer. Okay. Now, the limits we just did because I made them up. There's no real purpose to them. That's just what the question is. But the whole purpose of limits, initially why they were developed, is because what we really care about is slopes. Aha. So if we go to the next page, let's take a look at this. We're going to get down to right here today, okay? That's our goal. All right. So far, I know you guys have talked about slope before. Hopefully you know that lines have slopes. You can find the slope using a formula. You can find the slope if it's in mx plus b form. And slope is the rate of change. Okay? Slope also has special units we're going to talk about, how we know what the units of the slope are. Okay? Units in calculus really help us figure out what we're supposed to do. Okay? So that's something I'm going to harp on a lot. But what's the slope of this line? Sure is 3. Okay? All slope means is, if you have a point here and you go over 1, and all it doesn't make a triangle. You go over 1, you have to go up 3. Okay? And your line has to slope like that. Cool. Same thing as if you went over 2, you'd have to go up 6. Okay? All slope does is make a triangle, and they're all the same, similar triangles. Okay? Let me see here. It also means that, points on this line, like 0, 2 is on that line. If I plug in 10, I get 10, 32. Right, if I plug in 15, You get 15. I'm just picking a few points on here. 47. If you find the slope between any of those points, I keep making the points forever off that line, the slope will always be 3. Always. Okay? It's kind of a boring thing, just 3. All right? Which leads us to the graph of y equals x squared, which is a pretty basic function, right? We like him. Or her, I guess. That's not a line. That does not have a slope, right? But if I zoom in on it, I can't zoom in far enough in this document here, but if I zoomed in far enough on this point right here, 1, 1, what would it start to look like eventually? It starts to look like a line. And if it starts to look like a line, then we can find the slope of the line that it looks like. Does that make sense? The reason why that's important is, again, because slopes are rates of change. And the rates of change of things are very important in many aspects of things. Okay? How fast things are growing, how fast they are shrinking is always what people want to know. Okay? So really think about it in terms of like knowing the amount of something. I told you, like, I don't know how many kids are smoking Juuls or something, whatever. Okay? Like, okay, I don't know. Juul, I don't know. What is the correct verbiage for that sentence? Hitting? Yeah. Hitting Juuls. Okay. 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 Sorry. All right. Okay. All right. So if it was a very big number, right, you're like, oh, that's bad. But if I told you the rate of change of it was negative, you'd be like, right. As long as we all agree that hitting Juuls is not good. Okay. And what's even weirder to think about, okay, what if we said the number of students that are trying, Juuls, okay, is increasing? That means it's going up. But if I told you it was increasing at a slower rate, makes sense? So it's going up, but it's going up slower. So now not only am I talking about the rate of change of the amount, I'm talking about the rate of change of the rate of change. We're talking about how the rate of change is changing. Okay? So basically everything in the world is changing, and if you want to quantify that and calculate it, we need slopes, basically. Okay? All right. And there are many, 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 many reasons why we'd want to do that. Calculus, basically, if you study anything above this, calculus is like a part of it. Algebra is a part of all your math classes when you learn algebra. That's how calc's going to be for the most part. Okay? So anyway, we get this point 1, 1 that I picked, again, arbitrarily, and I want to know the slope at that point, because if I zoom in on it, it looks like a line. Okay? We could, just like we do with that line, pick another point on that parabola, right? If I picked -4, I would get 16, right? If I found the slope between, so can you pretend, like, if I were to draw a line that looked like the slope down here, it would look something like this. Does that make sense? That looks like about the slope of the curve right there. Okay? If I connected these 2 points with a line, does that look like that slope? I mean, no, it's stupid, right? Why would we do that? Okay? So we can't just pick any point. If I pick a point over here, look, I can even make the slope 0 if I want, if I pick this point. So depending on the 2 points I pick, I'll get different slopes. But remember we said we had to zoom in on that point to make it look like a line, which means if I'm going to use the point 1, 1, and I want to know the slope there, I need to pick another point that's really close to 1, 1. Makes sense? Like 0.9, 0.9, or even closer, 0.99999, like whatever that is squared. Okay? But we can also use the power of mathematics to make this easier and not pick a point at all. We can pick a variable point. Okay? Like so, and that'll give us a formula for the slope. Okay? So, here's what I'm saying to you. Rather than me picking a point like this point over here, -4, 16, which doesn't do me any good, let's make up a variable point, and that'll kind of allow us to play with it a little bit. So if I let the x value be a, what should we let the y value be? Sounds like b, right? But I'm tricking you. It's not b. Okay? Here's why. If I choose a for x and I choose b for y, where could that point be? Anywhere, right? I can pick 6, 100. I can pick -5, -20. But where do I need this point to be? On this thing. How do I guarantee if the x value is a that it's on the curve? How do you guarantee any points on the curve? What point was at -4? 116. Why do we know that? It'd be a squared. You got to plug it in. Yeah, we know what the y value is. So if I make a point a squared, that point's on that curve. Where is it? Depends on what a is. Make sense? That could be anywhere at all. What's the slope between a squared and the point I care about, which again, Glenn Smith, picked arbitrarily. Okay? We need to do the slope formula. y2 minus y1. Well, that would be a squared minus 1. Is that okay? Remember, our other point is 1, 1. And then over the x values changes, which would be 1 minus 1. No, a minus 1, right? So, someone tell me what that does. What is the point of this formula? If I plug an A value into there, what's it do? Someone tell me. Who can tell me? Raise a hand. Who can tell me what that formula does if I plug a number into there? What's it do?
Finds the slope between that point and the point you chose.
That's exactly what it does. It finds a slope between A, whatever I chose, and 1, 1. Make sense? I want to know what's happening at what point. Specifically, 1, 1. But what happens when I put 1 in there for A? I get 0 over 0. Oh no, it's not anything. Okay? So we'll define the slope at 1, 1 to be whatever that slope equation approaches as I plug in numbers closer and closer and closer to 1. I can't plug in 1, so let's see what happens when I plug in numbers really close to 1. But what's that reduced down to? Just A plus 1. Okay, now you're right, we're going to drop a limit in front of it. That gives us that notion of let's approach it. What does that equal if I drop a 1 into that? 2. That means if I put 0.9999999 into this, I'm going to get a slope that's really close to 2. Make sense? So the slope of x squared at 1 is 2. That's the basic idea, okay? And any function that's nice, it's called smooth, okay, and continuous. If you zoom in on it, it looks like a line, right? Some functions don't look like lines when you zoom in on it. We'll talk about those later on. But if it looks like a line, we should be able to find the slope of it, okay? And to take it one step further, and then I'll shut up. We just found the slope. If we plug a 1 in there, it's 2, right? Remember, this formula, the A plus 1, only finds the slope between 1, 1 and another point. I cannot use it to find the slope anywhere else. Like if I plug 7 into there, that finds a slope between 1, 1 and 749, if that makes sense. What's the slope between 1, 1 and 749? What would A, yeah, but what would A have to be if I want the point to be 7, 49? A would have to be 7. So what's the slope between 1, 1 and 749? 8. Yeah, A plus 1, that's it. If you want to know the slope to any other point, just add 1 to it. Okay, that's how the formula works. But it turns out that there's a pattern to the slopes at all the points. Matter of fact, there's a whole nother function that tells me the slope of x squared at any x value. Okay, I'll tell you what it is. It's 2x. If you double the x value of x squared, you get the slope. Okay, I'll show you why later on. Okay, but that is called a derivative. It's like a slope function. You can think of it. It tells me the slope. Okay, that's going to be a good chunk of our time this year. We're talking about those functions. Okay, all right. You have no homework tonight. So good. Enjoy your weekend, and hopefully